G Club at GPO here on the 18th of September. Who's running that one?
That'll be me. And
Again? Yeah.
it'll be on Chaos.
Okay, fantastic. 18th of September, folks, 7:30 start again. We've got another waterfall observing night on Saturday the 20th of September. So we've got the 13th of September, Saturday the 20th of September, both 5 o'clock starts, setups. And then Saturday 27th of September, if anybody's interested, there's the Macquarie University Astronomy Open Night at 5 o'clock. So Richard, you're from Macquarie, is that right?
That's right.
Will you be participating in that?
I'm on extended leave, so no.
Okay, yep, right, gotcha. All right, that's a big night. They have massive amounts of people. They're always asking for people to bring telescopes. All right, so if you'd like to participate in that, you'll get free entry and you'll get something to eat or something like that. Food, drinks. Just see me at the end and we'll get you on the right track for that one. Okay, Greg, are you there?
Yeah, there's more sausages available.
Right now? More food. So while I'm mouthing off, grab some more food at the back. Craig, did you want to talk about we obtained a grant?
Yeah, sure.
Go for it.
Just 2 seconds though. Can I just ask, because it's a good crowd here, who's here for the first time? Sure. So, and who? And you're not members? Okay, you will be late. That's okay. No pressure. That's all right.
That's next Sunday
I
morning.
think I invited them to come along to experience and then join up.
Yeah.
I know what it
Sweet.
is.
Okay, no worries. So this morning I went and picked this up from the club grants for the Southern Shire. So we applied for a grant for a defibrillator. So we got the money for that, which is good. So, and I also met a guy there who got a grant for his first aid course. So he's agreed that for the price of the defibrillator, he'll do the first aid course for us as well. So hopefully I'll organise that in the next few weeks. I'll send out a notice that we will be able to do that first aid training to make sure we know how to use our new defibrillator.
So, do you get just one question, do you get, is that what you've got a grant to do, just do the first aid course, or?
I got the grant for the defibrillator.
To get a defib,
Yeah.
defibrillator.
Does that-
So CPR, and you use it with CPR, right? Shock, in case you need to.
So are you doing your first aid course, or was it only just to use the defib?
No, first aid
Это я в
course, learn how to
обсерватории.
do CPR, a little bit of first
Это
aid.
люди, которые
And then, of
наблюдают
course,
за
how to
звездами
use
здесь.
The
Do you need
defib.
to pay for that, or?
We haven't discussed that yet, but can you ready? What are you thinking?
I think we'll be able to do it for free for the members.
Okay, fantastic, there you go.
Yeah, because I need to do a first aid course. that's
Done. All right, well, this will be an accredited one, but it's going to be in Craig's hands, this one. I don't know anything about it yet. Okay, thank you, Craig, Mr. Treasurer, Mr. Secretary. Would anybody else like to say anything before I introduce Richard?
Well, just one
Marty?
more thing. Are you having that gathering this year that you usually have down at Town Point Bowling Club, or what's happening there?
Oh,
Yeah, that.
the sassy get together.
Yeah.
Yeah, the dinner. That is in October, and I can't remember the date. It's not there. It's actually going to be at Boyle's Hotel on Sunday, but I don't remember the date. It's in October. It's in the, but it'll be announced next month,
Okay.
right? Okay,
When
so
you have to register that one.
it'll be later on in October, but it'll be announced at the beginning of October. Yeah, yeah, up to the day before.
Does everybody know there's actually a big event Monday morning?
Yes,
There's,
very good.
are you going to say?
Well, you can say.
Okay. Total lunar eclipse Monday morning. I think it starts 2:20.
Totality starts at 3:30.
So yeah, totality is 3:20.
3:20, there you go. And
Um,
finishes at about 4:45.
Yeah, there you go. So if you're an early morning person or a very, very, very late night person, total lunar eclipse. So because it's so late, it's actually going to be towards the west, not the east, as it has been in the past.
What time does it start?
It's the totality, so not totality, but the eclipse starts, first contact at 2:20, I think. Yeah.
and totality is around 330, something like that, and goes to about 445. Okay, so that's the circumstances. Greg, you got something to say?
Sausages are ready.
Good man. Okay. Jeff, thank you very much for the use of your phone just then. All right. Members, anything else from the floor before I introduce Richard? Okay. So, Professor Richard de Grace is a prolific public speaker on topics ranging from astronomy and astrophysics to maritime history. Richard holds professional appointments as a Professor of Astrophysics at Macquarie University and as Executive Director of the International Space Science Institute in Beijing. He recently published the first detailed biography of William Dawes, the astronomer assigned to the First Fleet from England to Australia. He was active 1787 and 1788 as the first astronomer here. His academic accolades include the 2012 Selby Award from the Australian Academy of Science. One of our founding fathers, we had two founding fathers. We had Frank Napier and Keith Selby, and that's Keith right there, right? Frank Napier. So, okay, we had a Selby here. It was a very important our society, they got it kicked off. A 2017 Erskine Award from the University of Canterbury, New Zealand, and the 2023 Excellence in Research Integrity Award from Macquarie University's Faculty of Science and Engineering. He also received the 2022 Blacktown Memorial History Prize and the 2022 Hella Meinheimer Award, Hecton International Journal of Medical Humanities. The sound of science, listening to the universe, so the synopsis of Richard's talk tonight. We are most familiar with what the universe looks like in normal light. However, the world around us, our sun, the planets, the stars and beyond, galaxies and even the leftovers from the Big Bang that started all, is abuzz with sounds. Sounds that we cannot hear directly, although we can transfer the signals we receive from this wide variety of astronomical sources to the range accessible to human hearing. Sometimes signals are mistaken for the telltale signs of alien civilizations. We explore the unheard side of the universe, listen rather than look. So without further ado, ladies and gentlemen, can you please give a warm welcome Professor Richard de Grace.
Thank you very much, and thank you, Lou, for the introduction. It's a great pleasure to be here in person. That's why I wanted to come. I mean, online talks, yeah, you can do them, but they're not so much fun. And I think you probably agree with that yourselves as audience members. Yeah, as Lou said, I'm Muslim. My main job is at Macquarie Uni, but at the moment, as I briefly referred to, I'm actually on sabbatical for half a year. It means I can do whatever I want and I don't have to go to the office, which is a fantastic thing to do. I happen to be in Sydney right now, so the talk can go ahead. But for instance, it's been 2 months and I spent a week in New Zealand at a conference, I spent 5 weeks in Asia. Part of that, my other job in Beijing, but my wife and I went on vacation to Uzbekistan for the first time ever. No idea what to expect, but it was the most fantastic holiday we've ever had. The people are warm, welcoming, such a fantastic place. And we went to Ulugh Observatory and Majdanek Observatory, which is the modern one. Now, the talk today will be about sound, but the eye wants something too. So I'm going to show you lots of pretty pictures as well as play a number of sounds. But before I do that, let me talk about what sound actually is. Sound is a wave. Now you're all familiar with waves on the water, they ripple and all that. That's not what sound is. Sound looks like this. Oh, no, of course not. Should work now. Right? You have, for instance, when you have a piston or anything that creates sound, that will disturb the particles in the air, and in essence, it will, in a way, kick particles forward and then go back and kick them again. So you get a wave, a higher number density of particles moving forward until they hit the eardrum. And because of changes in the pressure on the eardrum, you hear different sounds, in essence. So that's what sound is. So sound has, just like waves on the water, has a wavelength. So it has a typical distance between those two peaks, or the two troughs, that are successive to each other. And that's all we need to allow us to hear what the universe might sound like. Let's start by listening to what the Earth sounds like, and not what you and I sound like when we talk or when we listen to cars going by or planes taking off, but really the sounds of the Earth. And what better than to start with an earthquake, the Tohoku earthquake in 2011. These are, in essence, sound waves going around the Earth that can be visualized on this little picture on the top. But once those sound waves pass our measuring station, they get very loud, so be careful. Right? Those are some of the natural sounds of the Earth. Irrespective of what we do, what the wind does, this is natural. Sorry, I wanted to stop that to talk to you. Irrespective of what the Earth does in terms of earthquakes, when we go out, the first natural phenomenon that we can actually listen to are those beautiful auroras. The aurora australis, of course, here in the southern hemisphere, the aurora borealis in the northern hemisphere. And so what you just heard, I'm going to play it in a moment, are whistling sounds. So what happens? I'll show. Let's listen to it first. Right. That's what these auroras sound like. I'm going to move one on so I can actually talk over it. Actually, I can do that here. So what happens is the sun ejects continuously a lot of matter, particles streaming out from the sun into the solar system, and at some point those particles they're moving very, very fast, so they have very high energies. They're highly energetic particles. They hit the magnetic fields that's surrounding our Earth and that keeps us safe. And that means that all those highly energetic particles, which are very harmful to us humans in principle if they were all to hit the Earth right away, go in via the north and south poles. So close to the poles, you get this interplay of these highly energetic particles from the sun hitting the upper atmosphere, and you get those beautiful auroras. Now, people like yourselves, amateur astronomers and others, they actually chase auroras. They go and they try to listen and record the sounds that we just listened to. Now, the Earth is like a magnet, right? We have a North Pole and we have a South Pole. And if you have a magnet, you have magnetic field lines. They come out of the North Pole, they loop around, and they go to the South Pole. So here are just bits of iron scattered around a magnet, a bar magnet, with the North and the South Pole. Now, one thing that you probably do not know, because people often express surprise when I say this, we have a geographic North Pole. That's in the far north of the northern hemisphere. We have a geographic South Pole in the middle of Antarctica, and we have magnetic poles, which are roughly 10 something happens. I think we lost the internet. Okay. The magnetic poles are offset by roughly 10 degrees from the geographic pole. So in the southern hemisphere, the magnetic pole. On Earth, they go from the magnetic pole closest to the southern hemisphere, to the southern geographic pole, to the pole closest to the northern geographic pole. So the Earth has a North Pole and a South Pole, and a South Magnetic Pole and a North Magnetic Pole in the opposite direction. Right? So in terms of the magnetic poles, the magnetic and geographic poles are reversed, are opposite to each other. Here again are some of those whistler sounds that aurora chasers love to go after, and of course they're absolutely beautiful. We've seen auroras in recent years as far south or as far north as Sydney. They're called the Northern Lights as well. But as I said, there's lots of magnetism in the solar system, and this can be recorded by satellites. That's okay. I'm going to stop this briefly. What you saw there was an animation of the Bepi-Colombo satellite, which is a satellite launched by the European Space Agency jointly with the Japanese Space Agency on an orbit to Mercury, to explore Mercury. And that goes on a slingshot, and it's a long way, and it's going to get there by the end of next year. But while that satellite was going through the inner solar system, it passed all kinds of magnetic field lines associated with the planets in our solar system. And so the sound that you just heard, and I'm going to play it again, in instance was the sound of Bepi-Colombo passing across those magnetic field lines and hitting those changes in magnetism and highly energetic particles. So I'm going to play that again, if Right, so even the nearby universe is full of sound. Now the planets themselves, including the Earth, if you go some distance away from Earth and you have a very sensitive receiver and you point it at the Earth, you hear sounds. Not the sounds of people, trucks, airplanes and all that, but small quakes, things to do with the rotation of the Earth. And NASA did that a number of years ago. And this next video plays those sounds that the Earth makes. So these are radio emissions from the Earth, natural radio, vibrations, minor quakes. So that's what the Earth sounds like from outside the Earth orbit. When we go further out, we find the Moon. Now the Moon itself is quite a boring object. It's great to observe, of course, for amateur astronomers and for anyone to look at. But when the first Apollo astronauts went to the Moon, they heard some sounds they could not identify. My next video talks about those particular sounds and also why they have not been advertised very much.
Noises reportedly were heard in May 1969 by the Apollo 10 astronauts as they circled the Moon, a month before the first astronauts stepped foot on the lunar surface on July the 21st that same year. The three astronauts on board were Thomas Stafford, John Young, and Eugene Cernan. The sounds, which lasted about an hour, were recorded and transmitted to Mission Control in Houston.
I didn't need to do the sound on Stacy, didn't it? Do you hear that whistle sound?
According to the Discovery show, the trio felt the sounds were so strange that they debated whether or not to tell the chiefs at NASA, for fear they wouldn't be taken seriously and could be drafted from future space missions.
So
NASA says the sounds could not have been alien music. An engineer from the U.S. Space Agency said the noises likely came from interference caused by radios that were close to each other in the lunar module and command module. Astronaut L. Warden, who flew on Apollo 15, disputed that explanation, saying, quote, "Logic tells me that if there is something recorded on there, then there is something there."
Right, so the astronauts, even though they're highly trained, very technical people, clearly were superstitious as well. Right? They thought that these sounds that they recorded in orbit around the Moon were actually due to alien civilizations. 1969, Apollo 10. Now something else you probably didn't know. I'm going to now play another video showing you, or playing the sounds of the various planets in our solar system. And of course we know that the solar system is composed of 4 rocky Earth-like planets, Mercury, Venus, the Earth and Mars, and then the gas giants. And the difference in size gives rise to a difference in pitch as well. And I'd like you to listen to that. It starts with Pluto, and of course we all know by now that Pluto is no longer a planet, but the video starts with it anyway, so let's have a listen. So that is Pluto. And that is the natural sound you get from Pluto. It's fairly high pitched because it's a very small rocky body. And we get Neptune, lower pitch, much larger gas giant. Can anyone hear the sound in the back? Yes, no? Uranus. Uranus is of course has a smooth cloud cover, so there's not very much variation in the sound that we get from that planet. Jupiter. That's Saturn. I think I'll stop after this. So that's what rings sound like. And I think this is Venus. And Mars. Now, since all planets in our solar system have their natural sounds, if you at least know how to record it, what about other planets, other solar systems, exoplanets? This is a movie that's not actually the sounds of those planets, but it has put to music the discovery of all the planets orbiting other stars, extrasolar planets, over the years since the 1990s. And so I thought I'd play this for you as well, because it's kind of related anyway. So any little circle that shows up there is a new discovery of an exoplanet. Stop here for a moment, because you see suddenly this whole large number of planets showing up. This is the Kepler fields. The Kepler Space Telescope stared at a specific section of the sky for donkey's years and kept looking and looking and looking and found more and more planets. So that's why we have so many exoplanets in just a very small part of the sky. If you were to do the same thing across the sky, you'd probably discover an equal number of planets as found by Kepler. And then there are other areas that are maybe overrepresented. After Kepler, the main Kepler mission was over, the gyroscopes of the satellites, some of them stopped working. Kepler couldn't be kept stable staring at that same position anymore, but it could be kept stable looking at the ecliptic plane. And so they moved from the main Kepler mission to the K2 mission, and the K2 mission stared at some specific fields over time. And so we have a lot of exoplanet discoveries there as well. Now, this is not a talk about exoplanets, so I won't go into too much detail. We can talk about it later if you like. Yes?
Question, just about your definition of sound. How do you define sound in this situation? If sound doesn't travel through a vacuum?
Yeah, that's a very good point. Thank you for reminding. I should have said that.
Is it a technical word, the word sound? Is there another word that you use in a conference with experts? Or?
Now, what we do is we look at the vibrations, we look at the wavelength of the vibrations, and we convert that into sound, and that we can hear as humans. We can convert that into sound. We'll see later on in this presentation today, we'll talk about waves that are in essence referred to as sound waves by professionals, but they are billions of light years apart. And they are in essence 57 octaves in D flat below C minor or something like that. Anyway, so it's just a matter of converting the waves that we see in the universe to sound, so we can actually appreciate that the universe is actually it's quite alive. Actually, there's a lot happening there, right? That was the point of it.
Can I ask a question too?
in this, I consider this a work of art. What's determining the
because we're not quite at the end, and they put that to music. So that's just art.
the pitch is changing for each planetary discovery? What's controlling?
Yeah,
the
I don't
pitch?
know if it didn't say so, so I don't know what that was. Yes.
So those sound waves, are they ratioed up or down to bring it in the audible range? Or
Yeah, yeah, because it has to be converted to the human hearing range, otherwise you couldn't hear it. Absolutely, yes. It's overcheating, but this is a way of looking at the universe from a different perspective.
When you were showing the planets and the sound from the planets, was the sound normalised for all of the planets to the same frequency band?
No, it wasn't. It was moved to the human hearing range.
Right.
So my next video, in my next video, we go outside of our solar system. We fly to the nearest stars, and you might not know this, but every single star moves. It does not just rotate. It does not just go on an orbit around the Milky Way, but its surface goes in and out, in and out. Some of them are called variable stars. It's very obvious that they are variable because their light changes. But even stars like the Sun, they go in and out, but at a much smaller scale, a few meters per second perhaps. And that can be put to sound as well. So I'm going to play a few minutes of what the individual stars sound like as we fly through the universe to the Orion Nebula, the nearest birthplace of young stars. So what we heard there was, as we were flying through the nearby universe towards the Orion constellation and the Orion Nebula, we heard stars where the surfaces would be fluctuating going in and out, in and out. And here are some examples. Picture at the bottom left, you can see the interior of what's called the red giant star, a star at the end of its life, a very massive star at the end of its life. That's fluctuating a little bit. Those fluctuations get transported to the surface of the star, and they can actually be observed using visible light. So you can see what's on the surface, what kind of pulsations and vibrations the star is undergoing, and that tells us something about what's happening in the interior. That's actually a branch of astronomy called asteroseismology. And many stars, we can make models of how stars behave. And many stars show multiple modes of vibration and pulsation. And here's an example, for instance, of a star that it has all these weird and wonderful modes. Red is in and blue is out of the surface. So this has quite an interesting structure on the surface because there are so many modes of pulsation. These are called the fundamental mode, the first overtone, the second overtone, and you can go on from there. This can be modeled mathematically based on observations with satellites like Kepler, like the TESS satellite and other satellites specifically developed to study the surfaces of stars to try and understand what's happening right in the interior. And so in essence what you find, you can make a graph over time. This would be time, and that's brightness, and you can see over time that you have a fluctuation in brightness. And the fluctuation in brightness, in this case it looks a bit ratty, but it could be converted into something that has very specific wavelength, if you like, or peaks at very specific time periods. That's done at the bottom, that's quite complicated, but in essence that tells us how stars vibrate and pulsate. And that's what we heard in that video. That was just a conversion of those vibrations to the human hearing range. And different stars sounded differently. We saw, for instance, that very small stars had very high pitches, and very big stars, like piccolo, right, the instrument, and very big stars, like red giants, have very slow pulsations and very, very low pitches, more like a bass. So differently sized stars give rise to different vibrations and pulsations. And that can be used. Here's a graph that shows the temperature of the star along the horizontal axis and its brightness along the vertical axis. For very young stars, we have a high pitch. So we have a low pitch. The period between the peaks of those wavelengths takes almost 2 hours. But when the star gets older and older and older, the pitch becomes very quick, half an hour, 0.29 hour, so it's 20 minutes. So the pitch that we can determine the pulsation of the star changes over its lifetime, and that tells us something. Observing the frequency of that fluctuation tells us something about the age of the star. Right, so we, as astronomers, we cannot change anything in the universe, so we have to deal with the radiation that we receive and try to be smart enough to try and understand what really happens inside of those stars.
Excuse me? Does that mean that if you had two stars close together, you would be able to tell their size by listening to them?
By listening, yeah, by looking at those vibrations and pulsations.
Yeah.
Now, in principle, that you can do that, yes. You need to know their distance as well.
Yeah.
That's a fundamental parameter that you need. Yeah. Sorry, I was going, and this, what I was just trying to explain is explained slightly in a slightly different way in the next video. So I'm going to play this briefly. Those of you in the back, it says this is the sound of a star. Scientists can work out the star's size and where it is in its evolution, so its age. Dwarf stars, small. So you can see how the size feeds into the pitch that you hear. And so on stars like the Sun, we have sunspots, and in essence you can hear the sunspots because the surface is hissing. Okay, that's why I'm going to stop here. Going further out into the Milky Way galaxy, in the 1960s, it was found that some objects pulsate very regularly. And this is one of those objects that pulsated very regularly. And this object was discovered by a young graduate student at the University of Manchester in England, called Jocelyn Burnell at the time. She's now a very senior retired professor in the UK, very well known, Jocelyn Bell Burnell. But she, as a PhD student, discovered some objects that were pulsating very, very regularly, and they had no idea what kind of objects they were. They were somewhere in the Milky Way. Now this is what their first observation looked like. In essence, this is paper that goes through your machine, and then you see the peaks of the sound. Over time, you can see how it changes, right? Here it says 0 seconds, 10 seconds, 20 seconds, and you can see there are some troughs and peaks in that signal. And they put this all together, and so they found these peaks and troughs that were kind of regular, but not really. But that picture actually made it into pop culture. There was a pop group called Joy Division that brought out a vinyl LP, and of course that's their famous design on t-shirts and all that. But what was it? They had no idea what this was. So again, here is another observation obtained by Jocelyn Burnell at the time. They call it CP1919 or LGM1. Because I had no idea what it was, and they called it Little Green Men 1. Now obviously, it's, as far as we know, it's not Little Green Men. What it was is what we call now a pulsar. A rapidly rotating star, probably a star at the end of its life called a neutron star, that's going very rapidly around, that is ejecting very energetic material from its poles in jets. You can see that here, this is that neutron star, material being ejected along magnetic field lines. And when it goes around, occasionally, those jets hit the Earth, and it goes around, and once you've done a full rotation, you hit the Earth again, etc. Right? So that's what we believe pulsars are, like this. It's like a lighthouse, right? A lighthouse in the Milky Way galaxy. And we know of some of these lighthouses, some of these pulsars that rotate very rapidly. They rotate a full rotation on timescales of milliseconds. That is a millisecond pulsar. This is the pulsar in the center of the Crab Nebula in the Milky Way, observed with the Hubble Space Telescope. And when that was figured out, that they were not little green men, but they were rapidly rotating stars that had magnetized jets, they were probably neutron stars, and at the end of their lives, that actually led to the award of the Nobel Prize in Physics, not to Jocelyn, but to her supervisor. Marty Hewish got the Nobel Prize in Physics in 1974 for his pioneering research in radio astrophysics, Hewish for his decisive role in the discovery of pulsars. I have students, and when they do a lot of work, they are the first authors on their papers because they do the work. I don't do the work, I advise. So I don't think this was fair. Many people around the world, many professional astronomers today, believe that Jocelyn Bell Burnell, she didn't get the Nobel Prize, she should have gotten it. She has got lots and lots of other prizes, and she is a fantastic person. I know her personally quite well. We meet regularly, well, occasionally at meetings now. She's retired, she's getting older, of course. But she's always helpful, always willing to work with the next generation of young scientists. And she won a very big prize 8 years ago. She donated that entire prize to the UK's Institute of Physics to set up a bursary scheme for young scientists. And so she's the most fantastic person, and everyone loves her. She's great. All right, but we started this topic now to talk about the little green men. So let me talk a little bit more about alien life. And the Americans are, of course, particularly interested in that idea. And I'm not talking about area, whatever, so 40 something. I'm talking about the fact that they are trying to use the scientific method to find whether or not there are alien civilizations that are sending signals out. And they established an institution called SETI, the Search for Extraterrestrial Intelligence. And SETI has been fundraising for 30, 40 years. And they set up an array of radio telescopes, and here is an artist's impression of that, called the Allen array. The Allen Telescope Array. And they're scanning the sky in the hope of finding an artificial signal emitted by that supposed alien civilization out there. So what are the chances? Here's a question, look.
Yeah, Professor Shostak.
Shostak, yes.
Yeah, has come to our observatory twice.
Ah, okay, so you know everything about it.
So
Shostak is great. He was actually at my PhD institution when I did my PhD in the Netherlands. Yeah. Now, what are the chances of finding extraterrestrial life? And, well, we don't know. That's the simple answer. But in the 1960s, a serious astronomer, Francis Drake, came up with the idea of putting an equation together. So I'm going to show you an equation. It's not going to be anything difficult. He said the chances of the number of civilizations in our galaxy with which communication is possible depends on all these different parameters. And let me tell you, we don't know the value of any of those parameters with any certainty. Right? The average rate of star formation per year. So how many stars form on average? Well, we have a reasonable handle on that because that's what astrophysicists do. The fraction of those stars with planets. We're getting better at that as well. Most stars actually seem to have planets. We don't know how many have Earth-like planets or planets within a habitable zone. The number of planets that develop an ecosystem. Your guess is as good as mine, right? We don't know. The fraction of stars that develop life. We know that even less well. The fraction that develop intelligent life. You might wonder if there's any of that. The fraction that develop interstellar communication. Really? And then the lifetime of such civilization. So you can tell this is an equation that we cannot solve, that we cannot put a number to. And that was not the point of the equation. The point of the equation was to get this discussion going, right? Is there life out there? What should the conditions be? How should we look for it? And that led to nations around the world trying to do this. And of course, 1960s, Cold War, the Russians built a radio telescope. This is the Ratan 600 radio telescope. Massive circle and a line in the middle. When I was a first year PhD student in 1994, there was a conference in Russia. It was my first international conference. 15 foreigners and 15 Russians in the Caucasus Mountains. About a 2-3 hour drive from here. So one afternoon we did an excursion there. It was amazing, but at the time, this was 1994, the middle bit didn't work. And I don't think it has ever worked since. They have used this telescope, and at one point they looked with this telescope at an area in the Hercules cluster, and they found an object here, which they call Henry Draper 15668, that's the name of a star. And from that signal, this radio telescope, from that star, this radio telescope found a signal. This is the brightness increase in the radio. That happened once and never again. It was real. It's a big enough signal that it's real. Okay. That led to the idea that this is maybe similar to a signal that had been found in 1970. This was in 2016. A signal that was found in 1973, and that is now known as the WOW signal. Why? Because this was the observation at the time. They had numbers, right? This was what their brightnesses looked like. And suddenly there was this array of numbers that was suddenly much bigger than 1 or 2. And the scientists who found this wrote WOW on it. And that's why it's now called the WOW signal. I've got a brief interview on my next video with that particular scientist.
EQUJ5, the strongest signal I ever saw. That was exactly what we were looking for.
You can search a lifetime and never find anything. It can take hundreds or thousands of years for a signal to get to us.
It's hard to describe how modest our searches have been so far. I don't think many people have looked into it in much detail.
It remains unexplained. I don't believe there's been any real definitive evidence of extraterrestrial life.
Who knows what it was? We don't know what it is. And you can't say that it was aliens. You can't say that.
With my red pen, I circled the 6EQUJ5 and wrote the word WOW exclamation point.
It is the best evidence we know of coming from some other civilization.
Right, so professional astronomers in the United States still believe that this could be aliens. And I'm just dumbfounded when I hear those comments. But, I mean, that's not the scientific method, that's just, speculation. Anyway, that signal happened once, right? Happened once with the Ratan 600 Russian radio telescope. It happened once with this very old-fashioned radio telescope in Ohio. Now, you might know that over the last 20 years, 30 years maybe, a number of countries, international consortia, have been working on establishing a new generation of radio telescopes. That led to the establishment of the Square Kilometre Array Consortium, the radio telescopes. It's an international consortium that initially had 4 proposals to consider to build radio telescopes with a massive collecting surface of a square kilometre. Massive. The 4 proposals were 1 proposal from Australia, 1 proposal from Southern Africa, 1 proposal from Western Europe, and 1 proposal from China. Eventually, the proposals from Southern Africa and Australia were combined, and the square kilometre array is under construction in Western Australia and in the Carnarvon area of South Africa at this point. And it's on track to build more and more little antennas to eventually make up that 1 square kilometre surface area. The region in Europe was centered on the Netherlands, which is a key player has been a key player in radio astronomy for many years, but it's one of the biggest regions in the world. There's a lot of interference. In China, the Chinese were part of this square kilometre array. They were like, we need to do something ourselves.
Вот такое приключение в обсерватории сегодня. Они продолжают все рассказывать. Мне нужно ребенка отдавать чужого. Вот эта крыша такая, которая для наблюдения за звездами. Она открывается, и там большой телескоп обычно. Надо будет еще прийти и сделать трансляцию, как это все происходит. Пока буду заканчивать трансляцию. Увидимся в другой раз.